Hello, in this lecture on Laplace transform series, let me illustrate the use of initial and final value theorems by working out some problems. Okay, so now let us take some functions and we will try to find out the initial and final values of the function using these theorems. The question is, can you find the initial and final values of the function f of t whose Laplace transformation is given below? That means this f of s is the Laplace transform of some function f of t. It's given by this s plus 1 by s into s minus 1. So you have to find the initial value of this function as well as the final value of the function using these two theorems. Okay. So let us take first the initial value. The initial value f of 0 is by the initial value theorem will be limit of s tending to infinity of s into f of s. Okay. So this is initial value theorem. Okay, f of s is given here. Now what will be s into f of s? So s into f of s is this, s into f of s, s into s and s cancels, so it will be s plus 1 by s minus 1. Okay. Now let us substitute into this. So s into f of s is this, s plus 1 by s minus 1. In this you have to put s equal to infinity. If you put s equal to infinity, what happens is infinity, this becomes infinity by infinity. So when it becomes infinity by infinity, we can use L'Hospital rule. You can use L'Hospital rule, which is simply, the rule is differentiate the numerator, divided by differentiate the denominator, and then substitute the limits. So differential of numerator divided by differential of denominator and then substitute the limits. So differential of numerator s plus 1 is simply 1. Similarly, denominator differential of s minus 1 is also 1. So 1 and 1 cancels, so the value is 1. So the initial value of this function is 1. So the initial value of the function f of t whose Laplace transform is given here is 1. This we found out using initial value theorem. Without finding out f of t, we found the initial value using initial value theorem. Now let us go to the final value. Now this is the final value theorem. Final value is given by limit of s tending to 0 of s into f of s. But the final value theorem has also got a condition that provided that s into f of s should not become equal to infinity for any value of s satisfying the relation such that real value of s greater than or equal to 0. So let us see our function. This function s into f of s is this. So this function becomes infinity if s equal to 1. You will note here, if s equal to 1, s into f of s become equal to infinity. So let us find out the final value. For finding out final value, to use the final value theorem, what we find here, this function in this case s into ff becomes equal to infinity when s equal to 1, right? If s equal to 1, when you put s equal to 1 here, you put s equal to 1 here, 1 minus 1 becomes 0, denominator becomes 0, so the s into ffs becomes infinity. So because of this situation, we will not be able to use final value theorem, because final value theorem is applicable only when s into ffs is not equal to infinity, s into ffs should not become equal to infinity for any value of s satisfying the relation real value of s greater than or equal to 0. Here when s equal to 1, this s into ffs becomes infinity, so final value theorem cannot be applied. But final value theorem cannot be applied. We cannot find the final value using this theorem. Is not applicable, cannot be applied. Cannot be used. We have to find by some other means. We have to find what is f of t and then find the final value. Okay, so this is the point to be remembered while using final value theorem. To use final value theorem, s into ffs should not be equal to infinity for any value of s satisfying the relation real value of s greater than or equal to 0. Okay. Let us take another function, second function, ffs equal to 1 by s into s square plus 4. Okay, so here what will be s into ffs? S into ffs, if you multiply ffs by s and s cancels, you get 1 by s square plus 4. So initial value, by using theorem, initial value theorem, will be equal to f of 0 will be equal to s into ffs. You put s tending to infinity here. You put s equal to infinity here, this 1 by infinity, it becomes 0. So initial value is 0. Okay, initial value of this function is 0. So final value theorem, to use final value theorem, so here also you find, here what you find, does s into ffs become infinity for any value of s? Yes. Here if s square equal to minus 4 or s equal to plus or minus j2, where j square is means minus 1, okay, where j is root of minus 1, it's a complex number. So when s square equal to minus 4 or s equal to plus or minus j2, s into ffs becomes infinity. Right? We put s square equal to minus 4, 1 by 0 is infinity. So here also you find that for some value of s satisfying the relation, the real value of s is greater than 0 or equal to 0. So here in this case, what is the real value of s? Real value of s is here. This is only a complex number, this is only imaginary number. So real value of s is 0. So when the real value of s is 0, for a particular value of s such that the real value of s is 0, s into ffs becomes infinity. So here also the final value theorem cannot be used. The final value theorem cannot be used. Final value theorem cannot be used here. Final value theorem is not applicable. Okay. So let us take another function, third one, f of s equal to a into s square plus s square a divided by s square into s plus 1. Here s into f of s equal to a by s into s square plus 1. So here what happens? Does it become infinity? Yes. Here if s equal to 0, when f is equal to 0, s into f of s becomes infinity. So here also the final value theorem is not applicable. Final theorem is not applicable here. You cannot use final value theorem here, because when s equal to 0, s into f of s becomes infinity. Okay, but initial value can be found. Okay, initial value can be found, that is easy. So initial value is, what will be initial value? f0 equal to into s into f of s, put s equal to infinity. You put s equal to infinity here, what will you get? You put s equal to infinity, 1 by infinity, a by infinity will become 0. So initial value is 0. Okay. So let us take another function, fourth function, f of s equal to 2s plus 1 by s into s plus 1. So here s into f of s is 2s plus 1 by s plus 1. So if you want to find initial value, so this will be s into f of plus 1. In this we put s equal to infinity. When you put s equal to infinity, it becomes infinity by infinity. So you have to apply L'Hospital rule. L'Hospital rule is differentiate the numerator 2, differentiate the denominator 1, so it is 2. So initial value is 2. Now let us go to final value. Can we apply final value theorem here? Does s into f of s become equal to infinity for any real value of s? No, here s into f of s never becomes infinity. S into f of s never becomes infinity for any real value of s. For any value of s satisfying the relation real value of s is greater than or equal to 0. So s into f of s is always finite, it never becomes equal to infinity. So we can use final value theorem here. So and if you use final value theorem, by using final value theorem you can find the final value f infinity, that is final value means f of t as t tending to infinity will be equal to s into f of s tending to 0, right? So if you put s into f of s tending to 0, one is the answer. The final value is 1. So in this case we can use final value theorem. So when you use initial value theorem, does not have any rider, does not have any condition, it always can be used to find the initial value. But final value theorem has got a condition which has to be satisfied. So before using final value theorem, you have to check whether the condition s into f of s, does it ever become infinity? That has to be checked. So these 4 examples will illustrate the use of these 2 theorems and the condition. There will be more on Laplace transforms to be continued. So I request you to please subscribe to this channel so that you get notification of you get notifications of the new lectures, the new videos, the new lectures whenever they are published. Please share it to your friends. We'll see more later.